In a previous section, we saw that the equation of a plane containing the point x0, y0, z0 can be written as a times the quantity of x minus x0 plus b times the quantity of y minus y0 plus c times the quantity of z minus z0 is equal to 0. This can be rewritten as z minus z0 is equal to negative a over c times the quantity of x minus x0 minus b over c times the quantity of y minus y0. Our goal is not going to be to find a and c and b and c or anything like that. But before we move on, I'd like to remind you of an equation of a line in point slope form. If we think about y minus y0 is equal to m times x minus x0, then what we have is basically a three-dimensional version for a plane in R3 of what we see in a two-dimensional space, which is a line. Now that we've made that connection, I want to now connect this to what we saw in a previous video regarding partial derivatives. Here's a surface. Let's say it's z is f of xy. And we're going to consider a point in the xy plane, call it x0, y0. And associated with that point is going to be a point on the surface that I'm going to call P. And we'll say it has coordinates x0, y0, z0. We can consider two lines in the xy plane through the point x0, y0, one of which is parallel to the x-axis and the other is parallel to the y-axis. Above these lines exists a curve of intersection that would represent a vertical plane passing through these lines and intersecting the surface. In a previous video, we looked at partial derivatives using a picture kind of like this, but now what I would like to do is consider tangent lines. It took me a little bit to get that to look like a tangent line to me, but hey, it looks like I kind of nailed that one right away. The blue one holding y constant is a tangent line at the point P, and we're going to note that the slope of this tangent line, because we're holding y constant, right, we can see that it's above the line that's parallel to the x-axis, so a constant y value. The slope is going to be fx at x0, y0. Likewise, for the green line, which is another tangent line to the surface at P, and its slope is the partial with respect to y at x0, y0, because it's above the line that's parallel to the y-axis, and so is a constant x value, right? X is constant. Now, these are just two tangent lines at the point P on the surface, right? There are actually an infinite number of tangent lines, and they can go out in all directions. And if we were in a physical classroom, I would probably twirl a pencil onto some round object. But what you can see here is basically all of the tangent lines to the curve or to the surface that would intersect the surface at P. Now, folks, all of those tangent lines form a plane. And the equation of the tangent plane to the surface z equals f of xy at the point P given by x0, y0, z0 is z minus z0 is equal to fx at x0, y0 times x minus x0 plus fy at x0, y0 times y minus y0. We can connect this to, again, something that we've seen before. We can think of the fact that y minus y0 is equal to f prime of x0 times x minus x0 is the equation of a tangent plane to, tangent line to f through x0, y0, right? So in the case of R2, we only need to consider the derivative of f, right, f prime. But here in R3, we need to consider how z changes when x changes and how z changes when y changes. And so the combination slopes, if you will, are going to be fx and fy. Now we're talking about partial derivatives here, and we can say that a function f of xy is differentiable at a point AB if the partial with respect to x, fx, and the partial with respect to y, fy, exist near AB and are continuous at AB. Now let's find the equation of a tangent plane. Our directions are going to be find the equation of the tangent plane to z equals the natural log of x minus 2y at the point 3, 1, 0. Referring to the equation that we just saw, we need the partial of f with respect to x evaluated at 3, 1, the partial of f with respect to y evaluated at 3, 1, and then put that together as the equation of a plane. So the partial with respect to x is going to be 1 over x minus 2y. And I think I should be a little bit more careful with the notation. I'm going to say the partial with respect to x at xy is that quantity, or that expression. The partial with respect to y of xy, or at xy, is equal to negative 2 over x minus 2y. So the partial with respect to x at 3, 1, is equal to 1, and the partial of f with respect to y at 3, 1, my gosh, a lot of words, aren't there, is equal to negative 2. In terms of the colors that we have here in the equation above, fx is going to be blue, fy is going to be green, and we can start to put this equation together, right? We've got that z minus 0 is equal to 1 times the quantity of x minus 3 minus 2 times the quantity of y minus 1, bringing those colors back. And now we can kind of clean this up a little bit. Z is then equal to x minus 2y minus 1, or we can write it as x minus 2y minus z is equal to 1, and that's the one I'm going to box.